Okay, so we're going to find the zeros of this fourth degree polynomial function. So the first thing that I'm going to do to begin is by counting the sign changes in f. But we see that all the terms are positive, so f has 0 sign changes, and therefore it has 0 positive reals. Okay? And then we're going to look at the sign changes in f of negative x. And so when I plug in a negative x into f, I'm going to end up with this polynomial here. And we see that it has 1, 2, 3, 4 sign changes. Okay, so that means that f of x could have 4 negative real zeros, or 2, or 0. Okay, so each of these outcomes in blue, okay, these possibilities in blue will pair up with that in red. Okay, so now we're going to get a little chart here. And that chart is going to have 3 rows. So that 0 in red will pair up with each of those blue numbers. So positive real, negative real, and then non-real. Okay. So the 0 in red pairs up with the 4 in blue, 0 in red with 2 in blue, 0 in red with 0 in blue. Okay. Now remember that this is a fourth degree polynomial, so each row has to add up to 4. So if you have 0 positives and 0 negatives, you're going to have 0 non-real. Okay. In this case, you've got to account for 2 more zeros. Remember, each row has to add up to 4, and then 4 for the last. Okay. And then we're going to need to find our list of p's and q's. The p's are going to be the factors of 30. So I'm going to have 1, 2s, 3s, 5s, 6, 10, 15, and 30. And then the q's will be the factors of the leading coefficient, which will just be 1s. Okay. Now, what has to happen in general is that each of these p-values will get divided by each of the q-values, right? So I think you would agree that if you took all of these p-values and divided them by plus or minus 1s, you would just get back the p's. Okay, but knowing from Descartes' rule of signs that we will have 0 positive reals in every possible case, that means that we only need to now worry about the negative possibilities. So we're going to have -1, -2, -3, -5, -6, and so on. Okay? So that's very helpful. That really just shrunk our list of candidates down to half. Okay? So now we're going to, as our next step, we're going to see from this list of possible zeros which ones actually are zeros. And I'm going to begin by using the numbers with the lower absolute value. So I'm going to start with the -1. So now use the coefficients of f. And so we're hoping for a remainder of 0, right? And unfortunately, we don't. We get a 12 here. Okay? So that means that when you plug in -1 into this function, you get an output of 12. Okay? So it's not a 0. So that means I'm done with -1. And then we'll try the -2. Okay, now, every time I find a 0, I'm going to put it up here in this little top right-hand corner. Okay? So, put back in the coefficients of f and perform your synthetic division. Okay, so now 15 multiply, and then voila, we get 0. Okay, so f of negative 2 gives us 0, which is what we want. Okay, and now this is helpful because by the factor theorem, since f of negative 2 equals 0, then we know that x minus a negative 2, which is x plus 2, is a factor. Okay? So I think you would agree that if you had a factor which was x plus 2 and you set it to 0, and then you subtract both sides with a 2, then you're going to get the 0 that you see here. Okay? So I can always check that. Alright, now x plus 2 is one of the factors of f. And what is the other factor? Well, it's right here, the quotient. Okay? We know that the other factor is a third degree polynomial. Okay? So third degree times first degree is going to give us back fourth degree. Now, remember in class that I said that any time you end up with a factor that is a third degree polynomial, you're going to want to see if it's factorable by grouping. Because if it is, then you can finish the problem without having to do all this synthetic division here. Okay? It's a lot of arithmetic to perform. And we see that it is. Okay? Factorable by grouping. I'll do it right here in the top. So I can factor out an x squared out of the first two terms, and then I can factor out a 5 out of the last two, and then I can factor out an x plus 3 out of these two. Okay, so that's sort of like my side work there. Okay, now let's go back to our function f. I know that this polynomial, third degree, now factors into this first degree, x plus 3, times this second degree, quadratic. Okay? And we are just about done. Because now if you want to find the remaining 3 zeros, you're going to set the entire function to 0. Okay? We already know what x plus 2 will produce. It'll produce negative 2. Now we need to find the remaining. Okay, so set that to 0 and then solve for x. There's our next 0, negative 3. And then we're going to set this factor, x squared plus 5 equal to 0. And then we're going to subtract 5 from both sides. And can you tell me what the remaining zeros are? Okay, if you apply the square root to both sides, you'll see that x is going to be what? Plus or minus. You're taking the square root of a negative 5, and therefore your answers will be, that's right, imaginary. Square root of 5i, which will lead us to the square root of negative 5 will lead us to square root of 5i. Okay? And so those are the 4 zeros of f. And let's just go back and make one more observation, that you had this function f, and there was 3 possible outcomes for it, and it turned out that this was the outcome for your function. You had 2 negative real zeros and 2 of them that were non-real. Okay, so by non-real, remember, we mean could involve I. All right? And that's what we observe. Okay, hope that helps.